Thank you very much, and thanks for the kind introduction. Indeed, when I announced my lecture a couple of months ago already, I was planning for a talk on work in progress, on current research work, quite independently of discussions among people at the MECS. But now I changed my mind a bit, and I will try to connect and to contribute to the discussions at MECS. Hence I adapted my talk a bit. While the title is still valid, the published abstract is not. So, a common view on simulation. And this is, this coincides with what we heard in the introduction. Simulation is often connected to imitation, even to deceit. Exactly because one can take a simulation for the real thing. Because simulated phenomena are artificially like real phenomena. That would fit, if one wants to use a metaphor, it's like that simulation can be or is mirror-like, but maybe deceivingly so. Given that viewpoint, the title would be more fitting, the title for my talk would be more fitting as a slipping hazard, not a tripping hazard. Slipping because everything looks like, just plain, and the difficulty is to realize what is a simulation and what is not. So, I want to pursue in my talk this evening the opposite perspective to this perspective. That means I don't want to talk about the effects of simulation, like effects like keywords here would be the virtual reality. It's like reality, and what happens then, or immersion, or if you think of cultural critics like Baudrillard and the simulacra, stuff like that. That would be toward the slipping hazard. As I said, I want to pursue the opposite perspective and talk about more the origin or the creation or the construction of simulations. So that is, look at the process of simulation modeling and how simulation are made or are put to work as a medium. Let us go one step back and look at epistemology in general. Of course, we are all interested in the epistemology of simulation. So, epistemology in general would discuss questions like, what does count as knowledge? How do we gain it? How do we organize it? And one famous viewpoint here is by the philosopher Richard Rorty, who wrote in the late 70s a book called Philosophy and the Mirror of Nature. And his thesis is briefly that thinking that our knowledge would mirror nature is a profound and big mistake. This is the fundamental mistake of modern philosophy since centuries. This is exactly the critique of this mirror-like image that we connected, or I connected, with a common viewpoint. So the question would be, is there anything particular about simulation? If this is a general standpoint, is there something remaining? What could be the topic for the epistemology of simulation? And my claim is, yes, of course, there is an epistemology of simulation. It exists, and okay, does a special case at all? Yes, yes, yes. The claim is that simulation modeling deals with a problem of what I call the broken mirror. It will be, as I said, from a mathematical modeling perspective, and that broken mirror should suggest that it's more about construction than representation. I will explain more about the broken mirror later. The outline is simple. I want to argue or discuss characteristics of methodology, and I want to do that by discussing an extended historical example, climate modeling, namely. And then we learn some lessons from that example, and then I will argue that these lessons are in fact more general. This is a typical example in many respects. And then finally, there are some ramifications for epistemology. This is exactly about the tripping hazards for validation. So, let us start with climate modeling, with the global circulation of the atmosphere. Okay, you can imagine the atmosphere. It's a mixture of gases, but in physical respect, this is like fluids. It's fluid dynamics. And fluid dynamics is an old part of physics. So as early as 1904, the physicist Wilhelm Bjerknes, he was an assistant of Heinrich Hertz, he came up with a theoretical model. He was strong in combining fluid dynamics and thermodynamics and thinking, yeah, here we have all the theoretical tools to describe what's going on in the atmosphere, basically. And he devised a set of equations that would describe something like the laws of nature that govern the circulation of the atmosphere. Notably, this is a bit technical, I will not be technical in general here, this is a set of 6 equations, partial differential equations. So I don't go into the details here, but this is a sort, I mean, if you want to get out what the equations tell you about the behavior of the system, you have to integrate them. And integrating partial differential equations is, of course, difficult and often not feasible. And especially if you have a system like this one, of a nonlinear system, it's mathematically completely intractable. Bjerknes was well aware of that. It's more like a hobby of a theoretician. He was also a meteorologist and himself claimed, yeah, this will not be of use for meteorology anyway.
Intractable in what sense? Because it's like because it would take like a big computer to be able to solve it, or intractable meaning what?
You cannot.
Or it can be solved. It can be like solved in the full form. Or?
No, it cannot. It cannot be. Yeah. So you cannot.
Sorry, but
yeah. Yeah. You cannot integrate these equations, which would be, I mean, which would be the solution in general. But this is, you cannot do that. These are still called today the primitive equations of circular of atmospheric dynamics. And if in climate science, if one says what is the physical basis of climate science, it's indeed these 6 equations. Things changed, of course, with a new medium, with a computer. That was 5 decades later. And Norman Phillips was the first. He was working at Princeton with von Neumann and others. And in '55, he conducted the first simulation of the general circulation of the atmosphere. what did he do? He did two things. He discretized, more in a moment, he discretized this set of equations, plus used the computer. Discretization is crucial here. What does that mean? Very roughly, I have a picture here. Imagine this function. It looks a bit uneven, at least. Yeah, I took some picture. Don't mind. And a discrete version would look like this. Yeah. So the task to integrate this, you might remember that from your school times. That integration would be equal to determining the area under the curve. But you can do it, yeah, you slice it and say, yeah, but I slice it and at each point I have one height, and so it's easy to compute this because this is rectangular. So I know how to do that. Slice it and then compute it and add it up. It's something like the integral here, something like the area. So that would be a kind of a discrete version of integration. Of course, is it exactly the result of integration? Yeah, not exactly. There is some, I mean, it's only roughly so. You might imagine if you make that finer and finer, you get closer and closer to the, say, the ordinary mathematical integration. Okay. With the atmospheric system, the procedure was similar. Yeah? Imagine you have a huge grid over the surface, and with these nodes here and several layers. Initially, Phillips worked with only 2 layers. So he had 2 layers of atmosphere and I don't know, something like grid of say 500 kilometers or so. Yeah? And so this is a number of points. And discretization means instead of describing what Bjerknes did, the atmospheric dynamics everywhere, you describe it only at these points. And then you have to revise at these points, how do they affect the next points. And the time would also be in steps. So next time step, what happens at the grid points? That would be the discrete version of it. Okay. This is then called a finite difference model. Not a continuous model in space and time. It's finite differences. So you have finite space and also finite time intervals. But then, of course, you have to ask what criteria determine whether this is accurate or not. In the easy example you saw with this curve, yeah, if you make it finer and finer, you get closer and closer. But for Phillips, I mean, he had something like 1,000 kilometers wide. Is that accurate? Would that be a picture of the atmosphere or not? Close enough or not? There is, in general, I mean, for most systems, there is no mathematical way, yeah, to find that out in advance. The only way, yeah, there is no, I mean, you can always say theoretical convergence. If you make it finer and finer, the grid, then you get closer and closer to the dynamics that the continuous model describes. But actually, you don't work in this ultra-fine environment. If you are finite, and every computer is finite, yeah, it is discrete, and how close are you? How good are you? There is no theoretical mathematical grasp on that. And the only thing, and this you will see more often in my talk, yeah, the question is, does the computer model work accurately? Of course, one has to ask that always. And the answer is, that depends on the simulation of known patterns or phenomena. So you know what the dynamics has to look like, and you have to test or experiment and observe whether your computer behaves like that. What are known patterns and phenomena for this general circulation of the atmosphere? Not easy to tell. Here's an example. This is a map by the German Seewarte, old map, and there is wind. Yeah, oh, I see, this is not a good resolution. Anyway, for example, you see here is a stripe where winds are generally from the west. This is called the westerlies, and it has been long known that this is quite stable, a stable phenomenon known by sailors and so on, nothing to do with modeling. This is just observation. And more schematic, it looks like this. Here is a band of westerlies, here are the trade winds, and these, this is the vertical movement, where the air moves like this in so-called Hadley cells. So this is observation. And the question then is, if you simulate, if you run your discrete model, will it produce patterns like this or not? This is, an experimental question for a simulation experiment. And this is what Phillips did, of course. Everything else would be worthless. And indeed, his experiment, the first experiment it was called, the first experiment in meteorology, it was a big success because the wind patterns actually came up, appeared like expected or like hoped for. So you imagine, you have the Earth and the Earth at rest, the atmosphere in two layers, and then the computer model says, now the sun is radiating, the Earth is turning, and wait, what happens? And what happened was this schematic picture of the circulation. Okay, but it was also a huge failure because after a few simulated days, the whole system exploded. All the patterns dissolved. There was something wrong in the middle and long term. That was discerned as numerical instability. This is a new phenomenon, of course. You need the computer simulation to realize this. And it shows us that of course, discretization is not strictly derived from the continuous mathematical formulation. There are, different options for discretizations, and some are numerically unstable. You don't want to, researchers don't like that, but this happens in the world of discrete algorithms and discrete models. That created a huge research project. What to do with numerical instabilities? And a main actor here is Arakawa, who invented something. He modified the basic mathematical description in a surprisingly fundamental way. I would say this is a first rank, what he did, a first rank theoretical achievement, but it's not regarding the physics of the atmosphere. It's an achievement regarding the behavior of discrete algorithms. So he could devise a model that is provably stable. So he solved that problem, but he made some deviations from the physics. And so there was a huge criticism at the time, but we need correct physics. What should we do with a stable simulation if it's not expressing the right physics of the atmosphere? Arakawa was convinced that that would not matter much. But this is here about the date. He talked about that in '62, but of course, again, the same question, does it matter or not for the behavior of a simulation model? Hard to tell. You have to try that. You have to implement it and observe how it behaves. That took Arakawa 4 years to do that. Imagine typing in machine code. This is extremely tedious. After 4 years, he he himself was sure, now this works. That was a good circulation model. So again, oh yeah, here the same questions. I'm getting ahead of my presentation here. Yeah. There are others that did research on numerical stability, and of course most approaches were about how to avoid errors and how to smooth errors so that they somehow cancel out. This would be the normal strategy. But again, somewhat later, Johannes, one of the pioneers in numerical meteorology, he made a comparison of simulation models. He was interested in long run. So can these models predict years? So would they run stable for years? Arakawa versus others. And it came out, only then it came out. You see, it's again, you have to do it experimentally. Then it came out that Arakawa really won the competition because all other models that used smoothing procedures and so, they were in the long term much too periodic and too smooth. So the known aperiodicity of atmospheric behavior that was not shown, did not show up in these smoothened models. Okay, it's always the same refrain, like, yeah, does it simulate or, yeah, the known behavior, reproduce known behavior? Good, that much about the historical example. What kind of a lesson can one draw from that? We started with complexity, computational complexity in a sense, this intractable system of PDEs, a partial differential equation. This is in, say, the world is full of, if you want to describe physics and related examples by the traditional mathematics, the world is full of these intractable systems of partial differential equations. In this sense, the atmosphere is not a great exception. And of course, it is intractable with the means of the differential and integral calculus. One has to switch the mathematical medium, so to say, to treat such systems. Remodel them, maybe. If you start with such a continuous system, and I mean, yeah, later I say something. If you start, you have to remodel it to get a discrete version. So this is essential. The computer can only treat discrete things, time steps, discrete objects. So if you start with a theoretical model, a continuous model or not, you have to go through a discrete model. But then a gap arises. And this is, I should say, a gap arises. Because it's not only the question that how close is this discrete model, how closely related to the theoretical model, if a theoretical model exists. It's also regarding our grasp of behavior. Normally, mathematicians, scientists, or whoever cannot tell much about the behavior of discrete models. This is the great gap, that you have to try it, to experiment numerically with them to find out how they behave. But then, of course, you have to test how they behave, do simulation experiments. But then you end up in a kind of a slippery slope, because the more intense your test is, the more processes are required. For example, yeah, like in the climate, yeah, are the rain patterns reproduced adequately? Oh, okay, you have to model rain and clouds and all these things, yeah. So, because the observable phenomena are often very complex, the closer you want to get a picture of them, the more you have to insert into the simulation model, of course. Okay, before I come back to strategies how to fill this gap, I briefly resume. So the problem of validation is more like the question, yeah, is the gap filled adequately? And criteria for validation are, and here I deviate a bit from the introduction. It's not the essentials built in the simulation model, it's the fit to the observed phenomena. This is the criterion we can use. So validation cannot proceed by assuming a mirror-like quality of the simulation model. So even if you suppose that you have a theoretical model that expresses the laws of nature, but even then, the gap here to the discrete model makes it impossible to use the laws to validate the model, because there is this gap and you don't know, is it adequately bridged or not? Even if everything seems to be heavily theory-based, like in climate science, say this is the physics, this is fundamental, but is the discrete version right or not so right? So the gap prevents that. Instead, of course, simulation modeling has to or aims at constructing a mirror-like appearance. It wants somehow construct and modify so long until up to that the simulation model behaves in the right way. So validation has to show this mirror-like property, and all what one can do is to test against known cases, known phenomena, and to try to detect dissimilarity, seeing these are not the basic patterns we want to get from our simulation model, something like that. Of course, here this is a point for philosophical discussion. One should note that, because it's not obvious what known phenomena are. Last week, in Johannes' talk, we heard about these particle trajectories. But this is really an ephemeral kind of a phenomenon. And if you want to compare your simulation against these things, we learned that this is far from obvious, at least. There are other cases, like a few days ago I visited Berlin and the Hamburger Bahnhof. This is a museum for contemporary art, and there is a small exhibition showing some films by Harun Farocki. And he is a really sophisticated guy, I think. And they treat, these films all are connected to the military and to game and simulation. And there is one example. I don't know how he was able to film that. I have no idea. But it's a simulated, but a really, so in physically simulated Afghan village in a US desert. And Farocki says, and one could see that from the film, the village looks like it would imitate a computer simulation. This is, so it's far from obvious what known and accepted phenomena are here, But you have to, still you have to compare the two these. So validation is like, here I try to detect dissimilarity, is like a task for a falsification detective. We will see it's a mixture of Popper and Marx. Maybe you wonder what Marx has to do with our context here, but of course I will show you it's not Karl Marx, it's Groucho Marx. We have here a short video of the problem of the broken mirror. I hope that this works right now. So here, these are dubious spies. This is the real Groucho, and here he doesn't realize that the mirror is away, and this is a spy dressed like Groucho, and Groucho wants to test: is it a mirror? Is it a mirror-like image or not? What would you do as a detective? Of course, try different situations. Like that. Like, can simulation models reproduce the Ice Age? So this is really now the scientist thinking, the skeptical scientist thinking. And you can get more difficult, make it more difficult for your simulation model to reproduce the phenomena. This is severe testing. Severe testing, I would say. Okay, and now they start to play with a mirror metaphor. You know what will happen, but sometimes other things happen. Okay. Ah, there's another one, yeah. Okay. So, that was Groucho as a mirror detective. What is the more general lesson for the methodology of simulation here? And I would like to argue that this is one of the, at least in my opinion, of the important lessons about the methodology of computer simulation. And it would be that complexity and discretization are interrelated. Now, one guides to the other, and vice versa. Of course, in simulation modeling, you have to respect the conditions of the machine, the computer. Yeah? So, only discrete objects, only iterations. Yeah? But you can also utilize the conditions. You can have a huge number of processes and a huge number of steps, and do that quickly. So this is not for human beings. This is what the machine can do. Okay, and now I'm at the heart of my argument, so to say, the core of my argument, and this is now where my research really is ongoing here at the MECS and elsewhere. This interrelation, yeah, you can see that in the conception of modeling as well as in how software is produced. And in the conception of modeling, you can see it in the in parameterization and tuning. What does that mean? It's maybe think of an example. Yeah? Think of a climate again. Yeah? And I mentioned, yeah, if you want to have a more severe test, maybe about rain patterns, but then you have to deal with clouds. Yeah, you have a grid, and your model is at grid points, how to deal with clouds. Of course, and we heard from an older talk also that the cloud module is surprisingly small. But of course, you have to describe the effect of clouds. They are much more, I mean, the effect of clouds at one point of your grid. So how the cloud, all the effects of a cloud that is somehow vaguely dispersed in space has to be described in effect at one point. So you can introduce some parameters, like water vapor is transported or so. But what's the meaning of that? The meaning is, yeah, if you have this parameter, if you have the right value for it, the overall effect would be like in the real cloud. So in this way, you have lots of parameterization schemes and so on, but how to assign values, it's what one calls tuning, because the parameters normally have no direct physical meaning. Their meaning is the right value so that the overall behavior is adequate. So that means you end up, with more and more parameterizations and values of parameters that are chosen because they, in your model, they produce the overall behavior that you desire. Because it's not, say, from the bottom up. It's not like causal processes evolving in clouds. It's the global behavior of the model that tells you what your right parameter value is. But then, between all the parameterizations, your errors, they cancel out, or compensate, not cancel out, compensate, in a sense. Because if you tune one parameterization scheme, it's, say, on the basis of all the other parameterization schemes that are already in your model. So this is not simply clouds, it's clouds in a particular climate model with these and these assumptions, all the huge list. This is a big difference. Therefore, one cannot, in this situation, one cannot test parameterizations one by one. The tuning is for overall behavior. So this is kind of a complicated network of parameterizations that evolves here. And this is, by the way, in the example of climate modeling, this is a big methodological problem for climate modelers, because they know they have lots of parameterizations here, and they think this is maybe the main achievement of their institute to have worked with that. They have really a tradition how to do that. Hamburg does it different from Princeton, does it differently from Colorado, and so on. But how to compare that? Hardly possible at all. They can compare only the overall behavior of the complete model, but not the single parameterizations. With software programming, it's similar. You have also, everybody knows, what is a complicated system like Microsoft DOS. it often crashes, and even experts have no idea why. How can that happen? Normally, you have sophisticated modules that are more or less independent, and everything is tested, every module works or so. But then, in some situation, there is maybe some time pressure, and the program says, here this is not, there are some bugs in it, but I see every time all the values are just, I make up this example, are just, say, 5 digits too high. This is consistent. I tested it. I don't know why exactly it tested it, so let's subtract 5 digits at the end and everything is correct. This is true. But if 2 years later somebody else changes something at that module, the thing will behave very strangely. This is what software engineers call kluging. Kluging say this is a simple patch that works for the moment, but is not very principled. Complicated programs, complex programs are full of kluges. And if you, that might work, but if you change something, then often the reason for why this kluge works is not there anymore. And so this is like Rob's code. I think one can see it everywhere, and even in particle physics, like Rob's code. We changed this code, but it doesn't work. It seems to be full of bugs. How can that happen? This is Rob's fault, but Rob isn't here anymore. This is. I worked for a year in a bank in the software department. The same thing. The same thing. It's, I think, to everybody I talk to, it's the same thing everywhere. And this is a problem of constructing, often in division of labor, of constructing complicated software where say, the modularity somehow degenerates. So one ends up in a similar situation that the testing is of the whole system, but the entire system, but there is no, or it's getting harder and harder to see whether all the single modules behave well. So one could say this is a kind of a entanglement problem here. That as the system gets more complicated, the added parts, they are entangled in a way that makes it hard to single out the cause if something goes wrong. And so this is, so somehow, this entanglement problem, I think, is the key point of the interrelationship of complexity and discretization. Okay, as I told you, this is my, say, future project, to tell this story here in more detail with primordial examples and so on. I cannot do that right now. I have nice material sitting on my desk in the MECS. The next thing to do for me. So we move slowly towards the conclusion. I want to point out, there are important transformations in epistemology and methodology. I wanted to play around for something similar to miniature Wonderland. See that? You have, this was a great achievement in the 17th century. The continuous differential and integral calculus. That was, what enabled Newton to do his gravitational theory, and the Newtonian work, that became the paradigm of modern science. Really the paradigm. So we read that last week. Yeah, even Einstein was I mean convinced that basically if you come down to the real laws of nature, it has to be somehow in that paradigm. Leibniz was very clear. I mean, he did not invent the physics, but he at the same time invented the differential and integral calculus. He was, in a philosophical sense, very clear that the thing is, what was wanted was a kind of a medium that would enable, he saw the great success of algebra, of calculating with letters. This was incredible, because you can, you just name it X. You have no idea what it is, but you can calculate with that. And this is, he thought he wanted to get to something that would enable him to algebraically calculate with continuous geometrical objects. Okay, so that was the, say, in mathematics, a major methodological achievement. And you see that this was meant to create transparency, and it did, transparency and tractability for human operators. So that was the way that I mean, general laws, like they govern the motion of the planets, you have to be able to handle them. I mean, it's older than the differential calculus, but it took, I mean, people like Kepler or Copernicus or others, they devoted their life to getting through all these, I mean, data, amounts, that was nothing that had a great future, because as a medium it was more or less one could not achieve more with it. And this is quite different from the computer era, where one has this discretization and iteration. This is what the computer can do, only, say, iterative processes with discrete objects. And this, say, the change to simulation modeling instead of this kind of mathematical modeling here, that created, of course, tractability for machine, for the computing machine, but this is not made for humans. It's completely intractable for humans. So this is really, say, one sees here in the epistemology methodology of mathematical modeling and computer modeling, one sees a turn, say, the era of the individual, and so subject philosophy, caring of the subject, and so on. This fits quite well to here, but this is entirely different. Okay, therefore, it's, because this is not for human beings, they can only, I mean, somehow repair an image or construct something like a mirror, or something like appears like a mirror, but it's not that say, the inner workings, the correct, here one meant this scientific knowledge then, I mean, will be validated because it presents the inner workings of nature. Nothing here. This is only trying to mimic or trying to construct something that appears like a mirror. Okay, I'm right now at the conclusion. Tripping hazards. We saw the dilemma of opacity. So opacity, the counterpart of transparency. Let's say intransparency, opacity, and testing. Because simulation models are epistemically opaque, they require experimental testing. But a refinement of experimental testing will lead to an increase in opacity. So this is the dynamics here. And we saw that, by adding new subprocesses via new parameterizations, or adding new software routines and submodules, and so on. So validation can proceed not from the inner workings, but from adaptive success, I would think. And then, if this is so, the validity depends on the test cases and their, in general, unknown range of similarity. That means if you have tested this and that and this, are other cases that you did not test, is the model behaving well there? Sometimes it does, that you think, and there are many examples. For example, in engineering sciences, you think, they are so closely neighbored that for example, rules for bridge building or about statics, one is quite sure that one is in this range of similarity. One has tested the procedure sufficiently, and it's safe for similar bridges. It does not work always, as you know, but in that sense. Okay, so as I mentioned at the beginning, maybe one could start with simulation more as a slipping hazard, because it looks too real, and then one would be not aware of the validation problem. But if you go into the details, you see the validation problem, and if you realize that, you have to do with real tripping hazards, because that entanglement and opacity testing dilemma, this is really a stumbling block. You somehow, this is there, and I think it cannot be removed because it's part and parcel of the simulation modeling method. So if you ask me which one to prefer, I would go for the tripping hazard because it's better to fall forward. Thank you.